Hello and welcome you all for the next video lecture on distillation part 2. In this video lecture we'll be discussing on the different types of distillation. Here we'll be learning on simple and fractional distillation, steam distillation, tray column and packed bed distillation, azeotropic distillation, as well as extractive distillation. This particular topic I have divided into 3 different video lectures. Part A discusses on simple distillation and fractional distillation as well as steam distillation. Part B, I'll be discussing on tray column distillation and packed bed distillation. And in the part C, I'll be discussing on the next 2 types. They are the special types, azeotropic and extractive distillation. Before we get into these different types of the distillation, let us see what this equipment will do. This equipment can be operated under lab scale operation or industrial scale operation, or you can also operate it under batch scale or continuous. Lab scale in the sense you can operate only in the lab. Industrial scales you will operate in the industrial higher level. Large scale operation you will do it. Batch scale in the sense you will feed it and you will operate it, then you will take it out. Continuous means continuously feed is fed to the entire equipment, distillation equipment, and the operation is continuous. Just to remind you about the distillation process, how it works. You have a liquid phase and you are going to heat it and you are going to issue the vapor. You are going to get the vapor. The vapor is in equilibrium with the liquid phase. Now there is a more volatile component A and less volatile component B. We call it as a binary solution. A and B are present in both the phases. Now first you will be preheating the feed, the liquid phase here. It will reach its boiling point. Then sufficient quantity of vapor is issued. This vapor is in equilibrium with the liquid. Separate liquid and vapor phases you can get it. Most important thing is this A and B are present in both the phases, liquid phase as well as vapor phase. The difference is more volatile component will be rich, high in concentration in the vapor phase, less in the liquid phase. That is how we are going to separate it out. This vapor phase you are going to collect it separately and condense it. Now imagine a case where you have boiled the entire liquid phase. There is no liquid phase at all. If that is the case, you will get a complete vapor phase. The entire liquid phase is converted to vapor phase. In this situation, there is no difference in the concentration of liquid phase to vapor phase. Whatever you have in the liquid phase, everything will come into the vapor phase. In that case, there is no change in the composition of two phases. Right, let's look into simple distillation first. Now simple distillation, as you see, it's a laboratory equipment, laboratory design. Here you will be feeding the mixture in a small quantity and usually it is used for analytical operations. It has got one RB flask, one Liebig condenser. This condenser is called as a Liebig condenser, and you have a heating and cooling unit. Heating unit to heat the this particular RB flask where you are going to feed the input, that is liquid feed. And cooling system here for the Liebig condenser. You have a receiver flask here and a thermometer to measure the temperature of the mixture. Once you start heating the liquid phase, it will issue the vapor. The vapors are passed to the condenser. Now here to the condenser you have the liquid flowing in the counter current direction in the outer side. It is a two pipe heat exchanger, double pipe heat exchanger. From the annulus side the cooling fluid will flow from the tap. Through the inner pipe the vapor will flow and it will be condensed into the receiver flask. Usually it is a laboratory operated technique. Alright, I have a question for you. You can pause the video and just think about it and come back. Question is, how many equilibrium stages are present there? Alright, now I hope you have thought something, you have thought about this. Now the number of stages is one equilibrium stage. The reason is you have only one liquid phase and one vapor phase coming into contact with each other. You have, if you do not take it out, there exists only one equilibrium phase. But if you continuously remove it, you will get multiple equilibrium stages. The vapors are taken away and condensed. Now coming to the fractional distillation, it is something similar to your batch distillation. There is a small difference called as this particular vigorous column. Improvisation of your simple distillation. The simple distillation itself, you will be having your same design. You have a feed flask, condenser is present, thermometer is present, you have a receiver flask, cooling system, everything is same except for this particular column called as vigorous column, which looks like this. Now this column is usually filled with the glass bead. Now if you compare to the previous case, there was no much of space and it was the entire vapor was completely, it was moving on to the receiver flask. Now here you have the multiple spaces available where the liquid heating is not present here. So the vapor whichever is moving up, it may cool down and it may fall downwards by gravity, rolls down by the gravity. Now while coming down, the vapor which is going up after heating, the vapor which is going up, the liquid which is coming down, they come in contact with each other. Now that will increase the concentration of the vapor, that is whichever low volatile component which is going down, that will that liquid will come in contact with the vapor which has got high volatile component in it. More and more volatile component will move up along with the vapor. That is how the column increases the mass transfer stages. So you have provided more surface area, more the surface area, more chances of mass transfer. Mass transfer in the sense the liquid and vapor, they come in contact with each other. Whereas without this, if you take it, the vapor which is present inside this will come in contact with the liquid. Only this much surface area it will have. Now you have increased the surface area by providing more surface. This increased surface area ensures that there is more amount of liquid to vapor contact. This will increase the multiple equilibrium stages. The purity of the product that you get will increase. Right? So I have a question for you. Provides multiple equilibrium stage. What is the advantage of it? Just think about this and come back. Alright. I hope you have thought something about this particular concept of multiple equilibrium stage. The advantage is simple. It increases purification. Now imagine you have a feed somewhere here. If you do a single distillation, it is one stage. So this will be the composition. So you will have this much amount of vapor phase and liquid phase here. So one equilibrium stage only. Since you have multiple equilibrium stages here, so the liquid which is coming rolling down, when it goes up, it rolls down. So it will increase the equilibrium stages and it will ensure that it will increase the vapor composition. Final product that you receive in the receiver could be having very high concentration. If you have single that is equilibrium stage, that is simple distillation, if you have, this could be the product composition. This is X versus Y, this is temperature. I am showing you the boiling point diagram. Now the liquid whichever you have fed, it will have low concentration, sorry, the product will have low concentration for simple distillation. Whereas when you use fractional distillation, the number of stages increase and it ensures that the product has got high concentration. So the more pure distillate you are able to obtain using this method, but at the cost of energy. You require higher amount of energy for this. Usually it is used for multi-component distillation processes. Now let's look into the steam distillation. Now it's a batch distillation. You can use it under lab scale or industrial scale also available. It is usually used to separate immiscible liquids. It may be a little confusing here. Immiscible liquid, if they are immiscible with each other, why can't you remove it? The question is not that. There is a component which you are adding, it becomes immiscible. So you need to be very careful when you understand the concept here. Usually this particular process, steam distillation, is used for this particular application. Isolate temperature sensitive material. Second one, it is also used to remove the components that are high boiling. Imagine that you have a component which is having a high boiling point. If you heat it to that particular temperature, it may degrade. The component may degrade and it becomes useless for you. The product becomes useless. You can't heat it to that particular point, but you have to remove it. In that case, you will be using steam to distill that particular product at a lower temperature. How does this work? Let us see. Now, before we get into this particular concept, let me tell you some basic principle behind it. You take any liquid, pure fluid, any pure fluid you take, when its vapor pressure becomes equal to the atmospheric pressure. For example, at 100 degrees Celsius, the vapor pressure of water is 1 atmosphere, 101,325 Pascal. At 100 degrees Celsius, the vapor pressure of water is 1 atmosphere, P naught. Now, if you boil the water to 100 degrees Celsius at 1 atmospheric pressure, that means the atmospheric pressure becomes equal to vapor pressure. That time it boils. That's what we can see. When you heat the water, it becomes steam. It boils and becomes steam. So at atmospheric pressure, when its vapor pressure are equal, it boils. It's for a pure fluid. Now, if you have a high boiling liquid, boiling point is very high, you require very high energy to take it to that temperature. Say it is 150 or 200 degrees Celsius is a boiling point. You require very much high amount of energy. One problem. Second problem, you may be able to do this fine at the cost of energy, but the problem is this: the compound may undergo degradation. It may break down into its component products. Now, what we do, how we can solve? We will add one extra component, that is water. This water, when it comes in contact with this liquid, this particular liquid is immiscible with water. When you mix two immiscible liquids, one is water, another your compound of interest, it's in the liquid phase, this is immiscible with water. When these two come in contact and you boil it, they have their own individual vapor pressures, vapor pressure of water, vapor pressure of that individual liquid. The sum of these two will be obviously greater than the atmospheric pressure when you boil it to somewhere about 100 degrees Celsius, because at 100 degrees Celsius, at 100 degrees Celsius, at 1 atmospheric pressure, the boiling point of water is almost 1, and this will be, even though it is low, still the total will be more than atmospheric pressure. Most important item that you need to remember here: whenever you have immiscible liquid, Raoult's law is not obeyed. So the Raoult's law doesn't come into picture here. So the advantage here is immiscible liquid mixture boils at a temperature nearly 100 degree or lesser than that. Actually the boiling point is 150 or 200. Because of this particular condition, boiling point is decreased, that is boiling point is decreased below 100 degrees Celsius for this particular compound because of this particular principle, that is water and any immiscible liquid, when you boil it, it has a total vapor pressure lesser than the atmospheric pressure. So the boiling of this liquid below its boiling point. So if you boil a particular liquid at its boiling point, it will degrade, but we are boiling it at low temperature, that is at 100 degree. At this point it will distill as well as the compound is not degraded. This is the major advantage of steam distillation. Alright, I have a question for you here. Can you name an application of steam distillation? Just think about it. You can pause the video. Alright, let us look at about this application part. You might have thought of some concept, some compound which may be undergoing degradation or having a high boiling point. Before we get into that, just let us look about this particular concept, how it works. Now you have a steam generator, steam is generated, it is added with the liquid you want to separate. Now this is the feed mixture. This is miscible, the entire thing is miscible here. This feed mixture is dissolved here. Alright, the compound you want to remove, that is dissolved in some other component, A plus B is present. Steam is the third component that we are adding. This steam becomes insoluble, or you can say it becomes immiscible with the component A over here. The steam takes away the component A along with that over here, and it gets condensed in the receiver flask. Remember, water, that is steam, when you condense it becomes liquid water, that is immiscible with the compound that you take. A and this is C are immiscible with each other, which is condensed into the receiver flask. You know what will happen? By density it will separate out. You can easily remove by decantation, that is using a separating funnel. You can separate the steam and your product A. That is how the product A and B are separated at lower temperature. Okay, application. Right, you can isolate any essential oil or perfume from the plant using this method. So A is your perfume, component A is your perfume, component B is your plant extract. Another example is limonene oil. Most of the essential oils are extracted from like this, sandalwood oil. You just name any essential oil, it works in this particular concept. Now let us look at one example here. What will happen? Boiling point of oil is greater than that of boiling point of water. Oil is in very low quantity here. This is another problem also. This advantage for the steam distillation. Oil is along with other extract. So plant extract is present. Oil A, this is A. Plant extract is B. You will be adding steam, which is immiscible with the oil. That is how you will be doing the distillation. Steam, whichever you add it to the distillation flask, it takes away the oil, along with that condenses. In the recovery flask, you are separating it by gravity. Now let's have a video demonstration of this particular case, steam distillation of lavender oil. So you have a steam generator. It has this is the root extract, this is the plant extract, you can say. You have the liquid outside, that is the steam. The steam is heating it here, and the steam is taking away the lavender oil. Along with that, it goes through the condenser part here, and it is collected over in the receiver flask. Now the steam is produced here. This is the lavender flower, which has got lavender oil. So this is the boiler surface, and the lavender oil from the, this is the place where it going to generate the vapor. All right. Water, it is also used for heating also. It heats this as well as it produces the steam, two in one. So condensate, this particular vapor, it is condensed over here using a cooling system. The cold water in, cold water out. So in the counter current reaction, it is cooled. The blue colored one, the steam and essential oil, it is filled into this. You can see that water is heavier, oil is lighter. So by this is the product that is entering, it separates. The lighter component will overflow here. It overflows essential oil, and the water you get extra, you can siphon it off from this. All right. Now let us summarize the two topics. What you have seen in simple distillation, you have seen that it's a laboratory technique. The mixtures in a small quantity will be using. We used simple apparatus here and one equilibrium stage, you get it. In fractional distillation, you have seen that it attains a multiple equilibrium stage. The separation is better. You get a pure distillate, and most important thing is it consumes more energy. Steam distillation, you see in the principle behind it. When you add a steam, the boiling point of immiscible component decreases, and temperature sensitive materials, it's very easy to distill it, and also when they are low concentration. We have seen one example of this case. Yes, thank you.